Let us look at this, please, to see how we use the cut. No, the other one, Yeah. See? We use it. No, this is a function. So what it is, if I pass it by reference, by const reference, I will have to create immediately, right here, the first statement, I will have to create a new variable called inner counter equal counter. Otherwise, it's not going to work. It's an assignment right here. I cannot assign to a constant reference. Well, reference, then I'm going to be writing through a pointer to the outer stack frame. Why would I want to do that in a loop? I know you guys don't care about efficiency, but some of us do. That's the position of your management, don't you? Basically, if you use something often, bring it close. Right? You, of course, could use it through a pointer to a pointer to a pointer to a pointer to a pointer. But then it's not going to be close. You're going to, every time through the loop, you're going to go and extract it. So get it close. All right? Local variables are good. Inside the loop, you want to deal with things like this is an accumulator. Right? So why would you want to have a local accumulator? Because it's fast. You could pass accumulator by reference and accumulate in a far removed place, but it usually makes no sense. It's going to be slower. Yes?
I thought the reason why we have this precondition carry not equal to 0.
Yes? Well, because we don't want people to put zeros in, because you put a 0 and it will go and stick it. And it's and it will, 0 might not be combinable. Okay, let me explain. As we shall see soon, real soon now, well, speed we're going, we'll never see anything soon, but what happens is that we often use for 0 some funny thing. For example, in this min algorithm, it's going to be the last iterator to the range where we're finding min. So we don't want to do min applied to this so-called 0 value. So here we carefully avoid, by guarding it, by just saying precondition, don't do that, that we will ever do pass 0 and attempt to edit. Right? So 0 is a marker. We take great care never to apply operation. This is why in this guy, the second guy, we skip through 0 elements. Because we don't want to rely on the fact. Yes, sometimes indeed we could just add 0, will have no effect. But that will sometimes require unnecessary work, changing stuff. So this again, the sad fact is very often you fully see all these things when you use this thing like 55 times in different contexts, then you realize all the ramifications. So I'm explaining, but of course, look, I'm trying to derive everything in class. Right? But of course it's cheating. Hopefully you understand that it's cheating. That I know what we're deriving. It's not that it's not a random walk. It might appear as such, but it isn't really.
In that case, do you need to add a precondition to the add master class, or you do the
Yes, thank you. Yes, we need to carry exactly the same precondition. Yes. But we're not done with that method. And we're not done even with our dear constructor. because somebody was asking, I think the virtual Ryan was asking a question. He was saying, but do we really want to have an empty vector ever? Do we want to start with an empty vector? Yeah, we probably, if you're constructing this thing, then you're probably on a path of adding to it. And of course, vector will reallocate, but the first reallocations are going to be expensive. Allocations are in general expensive. So you might want to assure that you don't reallocate often in the beginning. And moreover, allocating one thing or 32 things effectively takes the same time. That's how life is. Malloc is pretty slow. So then we could rely on this fact, which you're the man. Yes, good. I'll get to you in 1 second. I remember. So.
I'm not trying to make you remember.
Yes. So let us think about sort of what should we do. Let us look at the constructor. Now you have to get the spoon. Couldn't we improve our constructor a little bit?
Do you mean by initializing the vector?
Initializing, maybe not quite. Maybe, you see, a vector allows you to,
Initialize the size of it?
not quite. You initialize, if you like, the capacity of it. You know how to do that?
Dot reserve?
Yeah, it will work. So what should we say?
Dot reserve, and then a number. And since
Tell us the number.
counter dot reserve, say 64.
I think you're excessive.
Okay, because most problems will, that's the upper limit.
That's the upper limit. Observe that if you outrun the upper limit, nothing terrible happens. One more reallocation will happen. And one more, if you reach 2 to the 32,
Okay. Yeah, okay, I got it.
I bring one more reallocation, I think you're not going to notice.
So 63. I agree.
Basically, I think that 32 is realistically more than enough, but maybe even 16. It doesn't matter. Because, you see, amortized cost of allocation is going to go down dramatically. So, yes?
We have no idea how big E is. So if you're going to do anything of this sort, you should allow the user to pass in a number.
You think? How big could it be?
E could be really big.
Like really like 128 bytes? Don't forget, you're not even initializing this thing. You're wasting, 10K on the heap. A totally unrealistic thing.
E is, segments of an image that I'm combining in some fashion.
And you're copying them by value. You should have studied things called pointers.
So the expectation is E will be small.
It's not necessarily very small, but how big. And again, we're not initializing this thing. Observe, this is not initialization. This is just telling vector. Yes?
I think we have to initialize it. Don't we have to fill it with zeros?
No. It's still empty. It's empty at this point.
Oh, okay.
Reserve changes capacity. capacity, not size. So what is guaranteed? That there will be no reallocations between now and then. So you will have to do 2 to the 32 steps to do reallocation. So Param might be right, and we will reduce. Okay, thank you. You read my mind. So that probably answers your objection.
No, I mean, you're right in that the rest of the interface assumes that keys are being passed by value anyway. So, yeah. You're passing keys by value to add and reduces returning keys.
Well, but they could, in any case, this is a different thing. When you have really gigantical things, guys, don't pass them by value use pointers.
I'm not agreeing with you. I'm saying
Yeah.
the entire
Yes.
design assumes that.
Yes.
You might as well.
Right. But this is not even, again, I just let me, since there seems to be confusion, even our experts who went through C++ course carefully, such as Bert, you just did. You went through 4 chapters. Bjarne's truth. He even bought the book. No, but you read the 4 chapters. No, you planned to read. I see. Guys, this is, everything starts with these good resolutions. So, but let me actually tell you. It's not essential to know C++. And guys, learn it. It's good for you, especially if you program in C++, not knowing the language. You can get by, as Bert convincingly proves. Yeah, all you need to know. But maybe you should learn a little bit. Okay. So when we do this, vector is still of size 0. There are no elements. The begin and end will still point at the same place. The vector is still empty. Of course, there is pre-allocated area. So then we push. We don't need to allocate more. Right? So this is why reserve exists. And this is why I'm stopping, because you need to know about it. It's helpful. You know, if you know how much you need, tell the stupid thing, it will pre-allocate. All right? Now, you are for something quite interesting. Now we have to take this thing and try to implement. Do you remember what was your homework, which I assume you did? Did you do the homework? No. This is very good, because that will give you the opportunity to do it now. Remember, our plan was, now we have this wonderful thing. We want to implement min element with the help of this guy. So it will be looking for min, just one min, not 2 mins, but in a binary way. Okay? Show him the code from CPP file. So if you were doing homework, you would have seen the file which Ryan concocted, which tells you that you need to write min element binary. And of course, his comment is no longer correct. You don't use add to counter and reduce. You use binary counter. Now we have a class. Okay, so you have this device which does this thing. How would you find minimum element given a range?
So define the minimum using.
You want to define a function called min element binary, which is a morally equivalent function to min element. Remember we implemented it in the class? But it's not going to compare first, second, then third, then fourth. It's going to do this in a binary way.
So we would, our op, we could apply this where our op is essentially finding the min of any 2 elements within the array. And then
First of all, let us write an interface of a function. It's always good, because then you will. So what's the interface of min element binary?
So, well, we have the name of it, min element binary, and then we have some sort of data structure, in this case an array.
No. We don't deal with things like arrays. This is some people who program in Pascal or whatever, maybe Fortran. We are advanced people. We don't need to know what data structure. We have been able to write algorithms without knowing data structures for 7 lectures now. What was the interface for min element?
So you want a pointer? Is it-
No, I don't want to point out. What was the interface for min element? We implemented it. 2 lectures ago?
Okay, so that, yeah, I'm an intern. I just got here. This is my 2nd week, so that was 2 ago.
Okay, this is fine. You might have, you know C++.
Yeah, I program more in Java, to be honest with you. So, but
Okay, so in C++, in Java too, by the way. Java guys learned from us. They never acknowledge, but actually if you look, they do. There's these things called iterators. You heard of iterators? That's what we use. We use iterators. You don't need to know whether it's an array, vector, list, set, map, whatever. And what we discovered that if we have something called forward iterator, we could write, Hernan, could you quickly show min element? Oh, you got it. Let us, Hernan will. Thank you. So, min max, it's right here. Down, 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 down. No, I don't know. No, it's min element. We wrote min element someplace. This. Okay, so we could look at it here. See, guys, we want something exactly like that. Literally exactly like that. Except that the algorithm will be different. Because this one just compares sort of the from left one by one. And we want to use our binary machinery. So we want to change the code, but we don't want to change the interface. So what we could do, what Hernan will do, he will copy and paste this guy. Could you copy and paste him to? Right, and change the name. And now we need to figure out how to do it.
okay. So, thank you. Let's see. So we need to. We can. There's the class itself that we created.
Which class?
The binary counter.
Binary counter, yes.
And the op is essentially the CMP.
It is essentially the CMP, but it isn't. You see, there's like, I'm essentially same as a gorilla. But I'm not really. Not quite. First of all, compare, what does compare work on? Yes, so. And what do we want, what is our operation? What kind of operation do we need for our machine there? But on what? Associative. And that is wrong. No. Guys, how silly you are. Think about it. What do we want to return? So the machine has to take an operation which takes two iterators and return an iterator. Otherwise, the machine wouldn't work for this thing. So let me suggest, when in doubt, you're going too fast. Let us try to see what we know. Let us see how you would like the code to look. Okay? You will say binary counter. Let me suggest something. You say angle bracket, and then you say dot, dot, dot. What does it mean? I have no idea. Because you don't, not really, not this very moment. Okay? And you call it something. What would you call it?
Min counter or something?
You could call it min counter, sure, why not? Min counter, yes. You constructed it. You got it. Of course, there is a problem. It needs to take some stuff. So, and then, but this is good. We don't know. We'll need to fill it. After that, what are we going to do?
After that, we're going to start to call some methods on it in order to.
What are we going to put in?
Well, we have to put the data in it that is by iterating through using first and last.
But we don't want to put data. We want to throw in the iterator.
Well, I'm sorry. Right.
Which is somebody, someplace will have to reference these iterators. But we don't know who. Because otherwise the machine wouldn't work. So what you would say probably is you will say min counter, and you will put something in it, dot. What? We have two methods.
Right. Dot add.
Yeah, so let's add something. What could we add? First, why not add first? Let's see how it works. First, and then I would actually put it in a loop. Because we want to add many things, right?
So while first.
Yeah? Yeah, see how easy it is? This is the main lesson of this class, is that whatever you do, you have to have a loop which says first not equal last. Yeah. Somehow the rest will happen. Huh? So this sort of makes sense, right? So you added all of them, yes? What should you do?
I don't necessarily think we want to. We're trying to do it using the binary counter, so we don't necessarily just add them all.
No, yeah, but this is our binary counter. It does it all for us.
Wait a minute. First of all, if we were going to do it that way, we'd have to put first plus plus someplace, right? In order.
What do you mean first plus plus?
Well, we're iterating over the yellow.
No. We need to do first plus plus here, yes. Or could put it on a separate line. If we like. Phew. Yes. Good. That's good. So we went through all of them. We threw them into the machine. Right? What do we do now?
Now we're going to try to reduce using this.
That's a simple thing because reduce doesn't even take any arguments. And I would even suggest that what we do, we go crazy. We return whatever the reduce reduces. So this is quite nifty now. Simple. We don't know what's going on, but somehow it works. Okay? So now we need to do what? Replace the dots. That's your broker, probably. No?
The 15 minutes, everyone's 15-minute alarm goes off at the same time.
Any suggestions?
binary counter, let's see, so the template is for type T, but in our case, are we going to apply I there?
Template type T does mean that this T is that T. It's some T. Yeah. I is easy. You know, when in doubt, cheat. Just name it something. Just name this class something. We'll figure out what it is. Well, it's not good to call it. I mean, we have this compare. So I would call it like min op. But I would say that the min op will depend on something. No, it probably will depend on its type. And we have only two types. Okay. Okay, so we sort of, so let's try using magic again. So what would you put here? How many arguments do we need?
Let's see, for the constructor, we need 2.
2. Okay, so we need to construct this operation. And to construct this operation, it's likely that you would need to know this operation, which is this comp. So I'm not even, I'm literally just showing you how you sort of struggle through when in doubt. Right? So you say you probably need to get min op of compare. Min op of compare, this guy. This guy. And you're going to give him this little compare. Min op of compare. It's just you're throwing in stuff. You say eventually it will work out somehow. You need, what is a good zero? What is a good zero? When in doubt, listen to other guys.
Yeah, last.
What else could you have? Yeah, first. First is clearly not a good zero because you will using it in computation. But last is clearly a bogus value because nobody last points past the end, right? So we'll just use it. Now, do you understand why I don't want to use 0 in my computation? Because it's some bogus value. Something like that. Now, of course, we need to define this class. We're almost done. It's pretty remarkable, guys, no? Or is it black magic? Is it black magic? Is this black magic? Bert. No, you're following? Okay. Which is hard? There are no hard parts. Okay, so we need to define min op class, it says. It's not a hard thing. So, okay, now we know that min op class is what kind of class? It's a template class, but actually of what kind? It's a functor, function object. It will take 2 what? 2 iterators, yeah, of some kind. Look at what they point to compare and return this or that depend. Could we write this code, you think, if we try? I think we can. Okay. So compares two iterators and returns the one which points to the smaller element. Make sense?
This is the part I had mental difficulty when I first looked at the STL library.
Ah.
When we just do the comparison, traditionally I think I'll compare two values.
And it always does. In STL, no. STL compares always to values.
All the values, but still,
This never appears in STL.
somewhere.
Nowhere. Nowhere.
But
So you might have had difficulty, but not for this reason.
okay, but I do see something compare and given to iterators and the return iterator somewhere.
Not me, somebody else.
Possible. But
Possible.
I think why on hell people do that? Why not just pass the values?
Because we're trying to return an iterator. You couldn't find an iterator back from a value. Like if somebody returns 3, you could never find out where the 3 lives. Not just in C++, but even in Java.
So this essentially is a kind of the concept of pointers, or wrapper of the value.
No, we're trying to find a pointer. What is the purpose of min element? Min element finds a pointer, an iterator, pointing to the smallest element in the range, yes? Now it returns a pointer. We talked about why. Remember, there were 2 reasons. First, if you return the pointer, what could you do? You could change it, right? I want to find the smallest guy and fire him, right? If you return a value. Second, it also solves this unpleasant problem with empty ranges, which is also not C++ problem. It's a mathematical problem. What do you return? What's the min of an empty set? I don't need to think about it now when I reduced it to pointers. So, but going back to these things, guys, we're going through the same territory again and again, but maybe we're making some progress. So now we need to try to write this guy. Pass the spoon. It's called the spoon.
Okay. Template.
Starts with T,
Let T.
type name.
Type. Sorry. Template type name.
What do you absolutely need to know now? What do you absolutely need to know now? You absolutely need to know some kind of compare.
Okay. So compare, but
Don't worry.
sure. Okay, that's all we need to do.
We need to name it.
Okay. Okay, min-op, or struct min-op
Is it struct? It could be struct.
class. It has no.
Doesn't it? Look at the code.
Yeah, it does. So, I'd say class then. Class. Min-op. Next, no braces on the next line.
But for sure, semicolon after the brace. That is, guys, remember, that's a capital offense.
So min-op will do a constructor.
What will it have? Will it have state?
We'll have a state. So we'll have a compare called CMP, if that's not too confusing.
And is it public or private?
Private.
It's private, it says.
Okay.
And will it have a constructor?
Yes. Copy constructor.
Not, well, copy constructor we don't need. Automatically provided for us.
Okay. So public min-op, compare CMP.
remember, we agreed that the main rule wins against partial rule. Const.
Yeah, const reference compare. Okay, and then colon, right? CMP, open paren, CMP, close paren, open brace, close brace.
Yeah. See, this code is so complicated.
Then
Here's the tricky one.
the
Why it's the tricky one? Tell them what's the tricky, what you have to think about.
how to pass the,
What don't you have? You just discovered that you haven't got something.
it's iterator type.
You don't have the iterator type. Because you see, we didn't put it. So was it a bug or was it design?
Mm,
We don't know it. So what do?
we have to add it.
No.
No.
You see, that's the beauty of it. We could templatize our application on it.
Okay. This
You
is
see what I'm saying?
no, not at all. This,
We are functorizing the thing. We are, okay, let me just help a little bit. We say template again, inside. You're going to have templates inside templates, and it works.
so type name I.
Right? And where I is some kind of an iterator. Huh?
And then what's the syntax for
What will it return? What will it return?
I?
Very good. What will it take?
It's going to take 2 I's.
And let's pass them by const ref, just in case. And the syntax, it's an operator application.
Operator open open close
Open, close. Huh? Call X.
X and Y, const I ref Y, and let's just return.
Here you have to be tricky. There is one thing. Remember, you have to assure the stability.
So CMP of X Y. No. Reference.
No.
dere-
No. You have to assure stability. When will Y win?
When X doesn't lose. So no, when X.
Y will win only when it's strictly less. Do you see what I'm saying? Therefore, you have to say,
I see. So if
these are little things, guys, but the world of programming is
try.
you have to dereference, yes, but what do you dereference? That was my question.
X.
No, because it's only when when Y is less.
Yeah. Then dereference X, colon, and ternary operator.
Very good. So if Y less than it's Y,
Right, Y, colon, X, semicolon.
guys, there are brilliant people like Nick. They write ternary operators. You guys write if then. I could read them. I could write them nested with no problem. But do not. People might be coming from Haskell. They will have difficulty. No, this is fine. This is fine. Okay.
So this is all really beautiful,
Mm.
but what does all the abstraction gain us?
Now nothing. Don't forget, we're on a long path. Well, first of all, it assures that the winner is going to play log n games. And that will allow us to finding. We'll get to that. First, we need to figure, okay, guys, everybody, literally, I have no time to do it. I was assuming that we'll do it. You have to compile it. You have to understand this code. You have to understand this code, because right now, if you don't understand this code, we cannot make any progress. You don't have to write anything. You basically have to take this code, compile it. There might be some bugs, right? But bugs should be trivially, right? And then the next time you will see what it gains us, all this machinery. It will gain us finding the second min quickly. We'll, of course, have to change this operation. So let me just quickly, before you go, tell you the idea is that we will instead, it's fundamentally, we're going to do this. The beginning of our algorithm is going to be just this, exactly this. But instead of this operation, we will have an operation which does this thing, exactly this thing, but it will also keep a tab of who won. Every guy will have a tab. I have a little list. Mikado. Yeah?
Can we take in a const and not, and then we are returning that, but it's not a const?
What? No, we're returning value. This is fine. I mean, we're returning value. We're not returning. And don't forget, these are iterators in a sense. We're not. All right? So the next, and for those who want to go ahead and try it, I told you the path. So the path is making little lists. Because without making little lists. So, and the next thing we'll actually have to figure out is how to make little lists. We'll have to forget about all kinds of reductions, all kinds of minimums. We'll have to work on implementing Lisp in C++. But really nice, elegant, clean, and exceptionally fast. Don't tell me that it's there. It's not in there. Right? So, because we don't need containers. Containers are bad old hat. Some idiot invented them in the early 90s. It's not what we want. Right? Again, one of the things which there's a major controversy. Like Dan and I always argue. Dan thinks that I should just tell you what is in STL. And I don't want to do that. I want to teach you to think so that you could design something equal or better than STL as you go. So I'm always showing like none of the algorithms which we're building are in STL. Well, it's not true. They're actually inside some of STL algorithms, but they're not exposed. Right? We're going to build some non-container type data structures, which are very useful, but they're beyond what the standard committee would ever consider. But they're awfully fast. So, right? This is what we're going to be doing in order to do this simple problem. You say, why, Alex, we're doing this simple problem? Couldn't you show us how to build a search engine? No, guys, I cannot. That's the problem. Not in a class. Right? So I could pick a problem which is small, which we could do in the class, and decompose it. So just, it makes sense. At least I think that it makes sense. But bye-bye.